If not,
I am here.
Okay, so that should be okay. Well, thank you so much, James. I'm very, very excited to hear about that funding and looking forward to hearing more about it. So with that,
Dashun can talk more about the conference. I hope he's co-organizing this with me. So
awesome.
And secured
10 years. Or the next 5 years. I think it's 5 years funding. No.
Is it 5 years? I think I was just fantasizing about the 10 years. I think that was just a dream, that I had. Right. So 5 years, 5 great years.
Yeah.
Maybe it's 3. I don't know, but couple of years, and then it's gonna run by itself. It's gonna be so much funding.
100 years.
Great. So we'll see you, James, in the panel session later. And
that's right.
Thank you. All right. So let's move on quickly to Dashun's talk. So I'm going to give a brief introduction to Dashun. You're probably, well, he doesn't probably need any introduction, but I'll say a couple of words. So Dashun is an associate professor of management and organizations at the Kellogg School of Management and the McCormick School of Engineering by courtesy at Northwestern University. At Kellogg, he's the founding director of the Center for Science and Innovation. He's also a core faculty at the Northwestern Institute of Complex Systems, NICO. His current research focuses on science of science, and you're probably familiar with his book, and now, from what I understand, is freely available to download. So without further ado, Dashun, please. There is no way for me to tell you when your 30 minutes are up. In total, you have 45 minutes. So, but go ahead. Thank you.
All right. Okay. Good morning, everybody. It's a real pleasure to be here. Now, let me see if the screen sharing is working. Now, it works?
It works, yes.
All right. Okay, great. Thanks, Daniel and Stephen, David. Good to see you again. It's been a long time. I think last time was probably, one of the James Evans things we're hanging out. So it's been a while, and thanks for doing this. This is fantastic, and I'm so excited to be here. So hi, everyone. My name is Dashun. I'm the recovering physicist at Kellogg. So here we just founded, and I'm currently directing the Center for Science of Science and Innovation, which is among the first center worldwide dedicated to this field that many of us now call science of science. So I think for the group of people here, it doesn't really require introduction, but this is a summer school, so I thought just put one slide here, which James probably talked about. In some sense, it is a very old field. Is also some senses a new field. So I think it's good to actually now have a group of very young researchers together to think about this field. So in some sense, I think a couple of milestones in recent years, in my mind, I think 2018 we published a review paper, Science of Science in Science. Later that year, Science also put out a special issue and putting us on a cover, arguing toward a more scientific science. And earlier this year, we're also excited about the publication of the first book for the field, The Science of Science. Don't buy the book. Well, feel free to buy it. If you buy the paper copy, which is much, much cheaper, but you don't have to buy the book. Go to my website. It's all freely available for download. And hopefully this is a resources as a sort of a quick introduction that's relatively accessible and synthesize a diverse set of lead research will give you a flavor of what are things that are overall happening in the field. And then, the field is very rapidly evolving. So, keep in mind, the book was published this year, but there was COVID. So I finished the book about 2019. So a lot of things happened since then. So, hopefully we'll be able to update it soon. And another thing I think that will be useful is, we'll also with time integrate a little bit more teaching materials such as slides and so on. So everybody can also see how to sort of present these materials included in the book. The goal is then make it easy for everybody to learn as well as to teach, okay? So I'm sure you covered a bunch of things in the past week. So I just want to emphasize two things that I find is very exciting and sort of very orienting in the way I think about the field. First of all, the idea of turning the scientific methods and curiosities on science itself, this is not a new idea. Okay, so this idea goes back to at least mid-past century, thinking about several founding giants for the field, such as Robert K. Morton, the great sociologist of science, thinking about the idea of massive effect, singletons and multiples, or the Sala Price, a physicist turned historian of science, thinking about the idea of invisible college, power laws, cumulative advantage, or Harriet Zuckerman, another sociologist of science, taking an ethnographer approach to thinking about, scientific elites, the careers of scientific elites, or Eugene Garfield, who is the father of Science Citation Index, or Thomas Kuhn, is one of the greatest thinkers in the 20th century, thinking about the idea of paradigm shifts, right? So in many ways, I think the new surge of interest in science of science is basically standing on the shoulders of these giants, but then take two things that they didn't have the luxury to have in their time, right? The first one is the increasing availability of large-scale data sets that trace the entirety of the scientific enterprise and their interactions, and helping us capture its inner workings at a really new level of scale and detail. And this is where one first important point I want to make is, the way we think about the field is progressing, I think right now is at a very exciting inflection point, because, when I look back our group's work for the past 5 years, it was very clear that every year our research agenda is driven by a new data set that just became available this year. And we didn't even think it was possible the year before. I think it was the case this year, it was the case the year before, and the year before that. Every year it seems like that. So I think the rate of new data sets that are becoming available these days is truly exciting. And this should be something that particularly exciting for young researchers in the room. And the second point is to think about the remarkable parallel developments in fields like network science and artificial intelligence over this past decade, which then offers us a wide range of tools that help us make sense of this growing data sets with growing accuracy and robustness. So I'm sure James talked about some of his AI work, and we'll talk about some applications of AI today as well in thinking about career patterns. But this is where it's really exciting. On the tool set, we also have this remarkable set of tools that are really, really strong and accurate and robust in a way that was hard to imagine just a couple of years back, right? So combining the data and tools together to tell a complex but very insightful story about how innovative careers unfold, how collaborations come together, contribute to discovery, and how scientific progress may emerge through different interconnected factors. So today I want to focus on one line of research, meaning thinking about career dynamics and what are the patterns of promising careers, and think about what are the major factors may be associated with major transitions within the career. And hopefully this is just one line of the overall research for the field, obviously, but hopefully give you some flavor of the things we're talking about. I think this traces back to a project we did initially a while back with Roberta Sinatra, close collaborator of mine. We start thinking about what are the patterns of promising careers. And I codename this project as the Hope Project, right? The idea is, when do you produce your best work? And, will you produce a better work after a major breakthrough? Or, are we dead, scientifically speaking? So if you think about career, a simplest way to think about scientific career, a simplest way is to think in this view of job pin view of a career, right? So every time you publish a paper, you put a pin at that location, and the height of the pin will tell you the impact of the paper, citations, for example, in this case. So then once you have this picture, then it's very easy to well define. And given every career, you can pick the tallest pin, right? So and then say, okay, so when does that tallest pin occur within the career? And this is a question, that's kind of the question of when do you do your best work? And this is a question that's attracted attention for many decades from psychologists and economists. And the overall picture is somewhere like this, right? It's somewhere, you peak somewhere in the middle, around 30 to 40 years old. and the logic is quite simple, is to think about, this is very robust pattern. So logic is, there's no 4 years old ever won a Nobel Prize, because, when you're starting, you have to learn. And then as you get older, then there's sort of growing duties, responsibilities stacking on your soldiers, reduce the time you have for research. So we measured it from our data. We're also seeing sort of a similar pattern. Somewhere in the middle, you peak, and then there is a very brutal decline as you get older. And in this case, we wanted sort of did basically a toy example. I want to think about a simple experiment. And the experiment we did was to say, why don't we take all these job pins, take 2 of them and swap them, okay? Just randomly swapping these. So when we do the swapping, what is happening? We're just doing the swapping. So we're keeping the total number of papers you publish fixed. We're keeping the distribution of impact of the papers fixed. When I'm swapping, I'm really just breaking the temporal correlation of when that bias work occurs. Imagine you have a deck of cards, and then you have an ace card between. I'm just shuffling the card, and now sort of wherever the ace card is, now is random within the deck of cards, okay? So then once I do that for all the careers, I can remeasure the same quantity and say, okay, if I think about, sort of randomized careers, where does the bias work occur? So what we find is that randomized careers seems to fall just on top of where the data shows, right? So this is where we think about, okay, although your bias work tend to occur somewhere in the middle, but that quantity is fundamentally intertwined with how much you produce over the course of a career. So if I randomize within the sequence of works, it seems like the bias work occurs is completely randomly within the sequence of work occurs. So that was main finding in the 2016 paper. It's called a random impact rule. And we find this is actually quite robust. So when we repeat this across different disciplines or across different time periods, what we find is that the peak always changes, depends on your cohort, but the fact that the real careers and the randomized careers tend to follow the same distribution seems to be always the case. And we actually then want to think about, okay, so can we build on this and extend this even further? So then we go ahead and collected a set of new type of careers that's similar to scientific careers, but has some different difference as well. So one, for example, we think about artistic careers. So we collect about 3,000 artists and their careers over the past 500 years. And in this case, sort of think about analogous to papers. Here, each artist produces artwork, and then the impact of the artwork is approximated by auction prices. And then we have movie directors, and think about each director produce different movies along their career, and then the impact of the movies is approximated by IMDb ratings. And then you have scientists produce papers. So across all these diverse set of careers, what we can think about is then repeat whether the random impact rule actually works. And in this case, we plot just everybody together as a cumulative distribution of within the sequence of works. What's the likelihood that this is your first work or last work or somewhere in the middle. And we also did this not just for your bias work, but also your second bias work and third bias work. So across all these different careers, across different hits within each different careers, we see a random impact rule start to emerge, actually remarkably consistent across these kind of careers. Now, so this, many people say, well, this is offering a very hopeful message, because what this is saying is that you're more likely to break through during your mid-career is not because age and creativity are intertwined. It's simply because you produce more during that time. So it seems like the message is rather hopeful, is that if you keep producing, although you're producing less and less over as you get older, but per paper hit rate seems to remain constant. So so this sort of offers a very hopeful message. Many people take it, but then at the same time, it also offers a very deep puzzle, because the question here is to think about what happens after you produce your bias work. Because I would like to think, if I do a hit work, I publish a major paper, that'll put me on the map. People may know me. I may get more funding, or if I published a hit paper, maybe I figured out some recipes, and all of this may help me to do another better paper afterwards, right? But if you think about random impact group, seems to portray careers as a lottery tickets, that every time you go and draw a lottery tickets, and thinking about then what this means is that after a major breakthrough, your next work actually is more likely to be mediocre than spectacular, because regression toward the mean, right? So what happened there? I think the puzzle then cracked open in a later paper we published, where we measured the correlation between your biggest hit and second biggest hit. So the idea here is to say, okay, if I know where your biggest hit is, I would know very well your second biggest hit is, because across all these careers, you see a very clear diagonal pattern occurs, that your second biggest hit just occurs around the corner of your biggest hit. And if you look at a first versus the third biggest hit, or second versus the third, you see a pretty much similar patterns, right? So what this is telling us is that the timing of each hit appears random within the sequence work you produce. The relative timing actually follows a very predictable pattern, right? So if you look at, okay, so then do these hits within the career actually more likely to happen consecutively back to back from each other? So in this case, we sort of basically draw a random line for each career, like think about medium, and we'll say, okay, how many works consecutively that occurs that are better than that threshold. So this is sort of to measure the length of your winning streak within your career. And what we find is that real careers systematically have longer streaks than what we would expect otherwise. So so that sort of tells us in real careers, high impact works also tend to occur back to back in sequence. So this raises the question, what mechanism is responsible for this observed cluster of hits in real careers? And so we find that most likely explanation is this ubiquitous yet unique hot streak that emerges randomly in your career. So think about you're starting your career at a certain level. Every time you publish a paper, you're drawing from a fixed distribution. As you progress at a random point in your career, all of a sudden you're elevated to another level. It's like you're not yourself anymore. It's like you went super saiyan. And you stay in that level for about 4 to 5 years, and then you fall back to where you were before. Okay, so if you this is a very simple model, it's very simple variation, but the intriguing part is that once we assume that model, we find actually it's very good to explain, basically explains all the patterns that we know about individual careers. And what's really interesting about this model is then, so this is called hot streak model. What's interesting about this model is then you can fit to real careers and learn a little bit about what hot streaks are about. So well, once we do that, we find a couple of interesting properties that may be useful for all of you. First, we find hot streaks are ubiquitous. About 90% of people have hot streak, but it's also usually unique. Most people have just one. We find hot streaks doesn't last forever. It usually is 5 years. And it's unassociated with productivity changes. It looks like you don't really produce more during hot streak, but it's just what you produce is substantially have higher impact, substantially higher impact than we would expect otherwise. So, hot streaks are, so once we have this, then we can actually do a bunch of other things. For example, now we understand a little bit of a new kind of a dynamics governing individual careers. If we integrate this with, how individual papers, as you're publishing them, what's the citation dynamics of individual papers, building on our earlier model we published back to 2013, then we can actually have an analytical solution for this kind of curve that we're familiar with. Think about Google Scholar curve is basically integrating hot streak model and then with the citation dynamics. And it turns out actually offers, despite the simplicity of the models, it offers a substantial predictive power in terms of thinking how do we model the career dynamics of individual scientists. So and we also think about this as a way to think about the idea of hot streaks is also fundamentally important for science policy and decision making, because in science, future impact is very important for a number of decisions, such as hiring, research support, and funding. So in this case, sort of what we want to think about is, if we want to have a good understanding of future impact, we ought to incorporate health streaks in our calculus. Now, there's major issues with this. So paper was published a while ago, 2018, and then at the time, it was a major limitation of the paper that I called out in OPED in Wall Street Journal shortly after the publication. And the idea here is to sort of a central question is, what is the mechanism? What triggers health streak? And so this was unknown, and it's been unknown for a long time, and it's something that really bothered me. And so this was a question that raised, shortly after the paper. And so to me, this is a central question, because if we have an answer to this question, it will actually potentially allow us to answer a range of new questions. For example, can we anticipate the start of a health streak? Can we create an environment to facilitate and promote the onset of a health streak, and to extend it when it emerges? And for someone who has had a health streak, can we treat that as an indication of their potential and think of ways to help them reach their potential, realize that potential again? So I'm excited today to talk about this new work. After 3 years of searching, I'm excited that we finally have some initial answer that seems consistent across a large variety of domains. And the epiphany came before the COVID time. I was at IC2S2 Amsterdam, and so I was visiting the Van Gogh Museum as an amateur art person. I don't know much about art, but I was walking through the Van Gogh Museum, and I realized, because Van Gogh is one person in our data set, and I know his health streak happened about 1888 when he moved from Paris to south of France. So that's where but I was walking around, I realized if I look at his paintings before 1888 and after 1888, I can, even for amateur like me, I can see some differences, but I can't put my fingers around what's the difference. But it told me that if we really want to understand what happens before and after health streak emerges, we should look at the work produced before and after and see if they are different, okay? So this is where we sort of collected a whole size of new data sets that we didn't have before, including, so now we have to look at not just auction prices of the artworks, we have to collect the images of the artworks and look at where they are, right? So in this case, we collected about 2,000 artists' histories, career histories, and about 800,000 images of the artworks that they produce, and combining data sets from two different sources. Similarly, we have about 4,000 directors. We combine about 80,000 movies that they produce, including the plots of the movies and the cast lists for these movies. And now we have scientists, about 20,000 individual careers, and we have like about 1 million papers that they produce. So as you can see, like this is obviously not any volume of data that anybody can just look through and figure this out. But luckily, sort of this is an illustration where AI has progressed to the stage that actually is becoming useful for answering these kind of questions. So in this case, to examine the art styles of artists, we use a transfer learning approach to construct an embedding space for artworks using a deep neural network. So in this case, specifically, we use this pre-trained VGGNet algorithm, which is one of the best known algorithms for image recognition. We applied it to image of artworks, and then we connect an additional layer, which is a fully connected layer, to classify art style labels in the data sets. So basically, we repurpose the image recognition algorithm to recognize artworks. So in this case, what's interesting is that once we can classify them, we can then analyze what the neural network is, the layers of neural network basically help use the neural network, help us see through whatever they see in the artwork. So the lower layers then captures low-level features such as line orientations or brush strokes. This is sort of what the neural network sees in the low-level features, filters, passing through this, and sort of this is interpretation overall. And in the higher layers, then it combines the inputs from lower layers and tells you sort of higher level concepts such as, shapes and objects, right? So then we can actually basically combine these and PCA into about 200 dimensional vector to represent each artwork, okay? So in the movie director case, we then sort of take two important sources of information for each movie, including what the plots are and also who are the casts. So basically for plots, we just did a word embedding on the plots and think about what are these plots are. And then we have, for the casts, we do a co-casting network and use a deep walk neural network on the thinking about a co-casting network. So then we have this 100 dimensional from word embedding, 100 dimensional from the co-casting network, and combined we have 200 dimensional vector for each movie. Similarly, for scientists, this is actually turns out to be one of the easiest domain. We did use a new deep neural network, but here I think the best method is to think about a recent paper published by Zhang and et al. In Nature Communications, where they look at the co-citing network of references. Like each paper have all the references. If you look at their co-citing network, and then that will tell you what's the topic of each paper. So we can look at that and think about the different topics of each paper. So once we have this machinery, then we can really sort of try to explore, imagine if we align each career based on where the house streak occurs. Do we see any patterns for works produced before and during the house streak, right? So a major hypothesis we test here is to think about exploration versus exploitation. So of the myriad factors that may shape career progression, the strategies of exploration and exploitation have attracted enduring interests from very broad set of disciplines. So this makes us wonder, if there's any potential relationship with health streaks. Okay, so in this case, then, these are exemplar careers in the data set. What we did is we apply so once we had an embedding, we apply a clustering algorithm and assign each style or topic accordingly. And then we just measure the entropy of the works in terms of different styles and topics before house streak and during house streak. Okay, once we do that, we find three primary findings in this case. First, we find that before a house streak, the entropy of the work is systematically larger than expected. Okay, here we're comparing the expectation with the randomized careers, where house streak emerges randomly within your career. So this means before house streak, individuals tend to diversify the topics they work on before house streak begins. So this is consistent with an exploration strategy in the period leading up to house streak. And following the onset of the house streak, we find that entropy measured in real careers become systematically smaller than expected. So suggesting that individuals become substantially more focused on what they work on. And this is better captured by exploitation strategy. And we find that despite the differences in the types of careers we study and the methodologies to examine their career outputs, this observed association between exploration and exploitation and house streak appears quite universal across all three domains we study. So this idea of exploitation during house streak makes a lot of sense if you think about the famous examples. For example, for painter Jackson Pollock, his house streak is the famous drip period where he developed a drip style. And so intensely focused on one topic. And Peter Jackson, for example, his house streak is a Lord of the Rings trilogy. Or John Fan, whose house streak occurred late for the ionization work that won him the chemistry Nobel in 2002. So this makes us wonder that maybe just the exploitation during house streak is the crucial ingredient. But if we just look at them, we go ahead and identify all the careers where they have a unique period of exploitation. What do we find is that if just exploitation occurs by itself, didn't have exploration that occurred before it, the chances for this to coincide with house streak actually is lower than expected. So this then suggests that, actually maybe the exploration that precedes a house streak is instead the crucial ingredient. So then we then calculated okay, when you just explore without exploit afterwards, whether that occurs, whether just exploration may trigger a health streak. And what we find is that if you just have exploration and didn't have exploitation afterwards, the chance for that to coincide with health streak is again reduced. So, and rather sort of is really exploration followed by exploitation is the only combination that seems to predict when health streak occurs. So what this means is sort of very interesting that we find is neither exploration nor exploitation alone is associated with health streak dynamics. Rather, it seems to be the shift from exploration to exploitation that closely traces the onset of health streaks. Okay, so one plausible explanation is that exploration as a risky strategy increases the chances that an individual stumbles upon new groundbreaking ideas. And the subsequent exploitation allows the individual to focus, develop knowledge and capabilities in that area, and build out their discoveries further. And importantly, this finding suggests that both ingredients of exploration and exploitation seem necessary. So this supports the notion that not all explorations are fruitful, and the exploitation in the absence of new ideas may not be as productive. On the other hand, the sequence of exploration followed by exploitation may facilitate the emergence of high impact work by incorporating new insights into a focused agenda. So the positioning of exploration before exploitation may therefore serve to expand an individual's creative possibilities. So this is sort of, I'm excited about this work because after so many years, we finally at least find one answer. So it's not the answer, but at least one answer that we have evidence for that's consistent associated with the onset of health streak. Hopefully this will also be a beginning of many follow-up works to also think about what else may be associated with the beginning of health streaks. I see I'm roughly about 30 minutes, right? So should I keep talking? I can talk more, or I should take some questions. I can talk for 5 more minutes, or I should just take questions.
There are questions already, but if you want to keep, yeah, maybe three minutes or 4 minutes.
Sure, let me actually just quickly, this is also published work. Another one that I realized is to think further about this idea of exploration and exploitation, and how exploration and exploitation help us think about career transitions, and not just transitions from normal state to health streak, but here I want to think about even more dramatic transitions, which is from failures to success. Okay, so I'm looking at all these examples of very successful people, ideas, and companies. I realize there's a major problem with this is that before you are somebody, you were nobody, right? So the question is, but when you were nobody, what's the transition that sort of help you think about you become somebody, right? So what is this transition from failure to success? And one of the greatest example is Michael Jordan's Nike commercial, is to say, I failed over and over and over again in my life. That is why I succeed. Michael is not a social scientist, so to excuse him for a very casual language here, but it does raise a question that success is often preceded by repeated attempts that initially fail. But how exactly do we fail over and over and eventually to succeed or not, right? So, and the reality here is that only some histories of failure lead to success. So this begs the question of which kinds of failure patterns ultimately yield results, okay? And conventional explanation about this centered around luck or differences between winners and losers based on their learning strategies and individual characteristics. And our results find also collaboration with James Evans and my team members is that the answer seems like it's not that simple. So here we sort of give you some intuition. So we study 3 kinds of careers of repeated failures eventually lead to success. First, as example, should be familiar with all the PIs in the room, and is to think about the failures in grant applications, right? So here we have all the NIH grant applications, R01s, the major, the largest mechanism in NIH over the past 30 years. So here thinking about individual PIs trying to get a grant failed, trying to get another grant failed, and until they got a grant or not, okay? So, and the second one is a serial entrepreneur example. Think about these are entrepreneurs participating in a company, didn't quite work out, and joined another startup, didn't quite work out, and failed over and over. Eventually, maybe a startup achieved a successful exit. And the third domain where we look at a negative example, we look at terrorist organizations. So in this case, we look at the terrorist organizations that launch an attack, but nothing quite happened, sort of failed, and then launch another attack until they actually claim some casualty, right? So that's kind of a negative example, but it helps us go beyond the innovation domains. Okay, so in across all this, sort of want to build one theoretical framework to capture a very simple framework to capture this kind of dynamics. Basically, it's exploration, exploitation type of dynamics. So think about each attempt, you have different components. And the thing with failure, which is interesting, is that we basically wanted to view failure as this wonderful thing that offers two crucial assets. First is that you failed, that means you tried. So there's experience, okay? Second, you failed, that means there's some feedback that tell you here's why you failed. So there's some feedback, okay? So the experience and feedback. So if you think about each attempt is different components, then you basically have different feedback, different scores for that attempt. And then now, if you want to think about, okay, I failed 3 times, I want to try the 4th time. What do I do? What can you do is just go back to what you had before and look at all the past attempts and see if these are good attempts. If the scores are pretty good, then you can just reuse the best one you had before. And if the scores are not so great, then you then you want to try it again and sort of create something from scratch. So this is sort of create versus reuse, or exploration versus exploitation. So with probability P, you create a new one, or and that has a random score, or 1 minus P, you reuse the past best version. Once you assume this very simple dynamics, you can parameterize the model based on how many past failures you look at, sort of approximates how much you learn from the past. What we find is a sort of a very interesting pattern that emerges from this very simple model. So the model shows that how much we benefit from failure or learn from the past actually doesn't follow a smooth path, but a very abrupt one characterized by phase transitions, sort of tipping points, separating a stagnation versus success region. Okay, so this is very similar to the physics, first order phase transition, physics transition from water to ice. Okay, so in the stagnation region, you learn more from past failure, but the learning is not enough. So what this sort of means is that when you just learn a little bit, but when it's not enough, then you hit a early saturation point. So you fail to engage in the intelligent improvement. So in many cases, you're basically throwing out all the prior attempts, although some component may actually be useful. But if you just learn a little bit more, you quickly transition into the next next region, entering the progression region. So here, individuals seek feedback to engage in the intelligent improvement. So it becomes yielding incrementally better attempts and ultimately lead them to victory. So those who eventually succeed fail much faster and increasingly fast with each attempt. So because they reused previous component efficiently rather than discarding the baby with the bathwater as their stagnant peers do. Okay, so what we find is that this phase transition, and sort of what that predicts then is a small microscopic change would generate a very large microscopic difference. So that means if you think about the individuals around the tipping point, they could be very similar in their luck or individual strategies, but they could be experiencing fundamentally different outcomes. So in some sense, then we sort of went ahead and measured it from the data, taking people who fail repeatedly and eventually succeed versus those who fail and then just disappeared. And you see these two groups follows very different dynamics. One group, the success group, fails increasingly fast, and the other group sort of stagnant, stays constant over time. So what this model predicts, and which sort of seems surprisingly actually is quite consistent, is, despite the simplicity of the model and diversity of domains we study, we find that people across fields predictably diverge into the success and stagnation group described here. And the interesting part is that these groups are actually of similar size and similar initial characteristics when they start. But once they start learning from the past, we see, fail, and we see they follow actually fundamentally different temporal dynamics that are actually distinguishable very early on. So this sort of hopefully is another view of thinking about exploration, exploitation, and career transitions from failure to success. And the paper was led by a PhD student, Ian Yin, who is actually right now on job market. It was published just before the pandemic in Nature. So I'll conclude there. So feel free to check out our websites, and grateful for a wide range of funders supporting our work, made all this possible. We're also hiring, as always, all the time at all levels. So please, if you're interested, join us, get in touch with us. Okay, thank you very much.
Thank you very much, Dashun. Always fascinating to hear. And now your new work with deep learning and things like that, very interesting. So lots of applauses virtually here on Zoom. So if there are any questions, please raise your hand. There was a question in the chat that I missed. So one question from Han, he asks, what do you think about the biological limitations of humans when researchers get older? Their energy should decrease. Can researchers do very intellectually demanding research in the last stages of their career?
I'm sorry, you blinked.
Like when you get older, it's harder to do intellectually demanding work. So how does that play into your idea of like career decreases in productivity and citations later on?
Yeah, so I mean, that's kind of the traditional view of one of the explanations why, as you get older, if you measure the chance for you to break through, that just decreases. It seems that the probability decreases. What we're finding basically is just to say, well, actually per paper, conditional on publishing, the hit rate actually stays roughly constant, and it's remarkably so. But it's very important to carefully interpret what that means, right? So it doesn't mean that if you just publish another paper, you will have the same probability, because there could be a lot of selection going on. Maybe you grow older, you're better at selecting papers. So you only publish the ones that you think are good, despite your declining intellectual power. I don't know, but it could also mean, you're intellectually staying like just constant, or it could also mean like it's harder actually for you to publish. So intellectually, you're actually better than your younger self, but but so you actually can maintain it. We don't know exactly what happened, but at least what we know is that per condition on publishing, per paper hit rate remains actually quite stable over your career.
Thank you. So we have a question from Hannah, and let me just say, I'm going to be the bad guy. Just try to ask just one question, please. Thank you.
I thought that the talk about exploitation and exploration was really interesting. And I was curious about how those communities change over time, and might exploitation in the community at the end of 5 years look like exploration in the community at the start of those 5 years?
You mean your case in particular?
No, just in general, like are you considering how the communities, the intellectual communities might change over those 5 years? Because the topics that you explore at the end, if you're going deep into them, that could be exploration if it were early in exploring that topic 5 years ago.
Yeah, no, that's a good point. Actually, this is something I struggle with writing the paper. Is exploration, exploitation is a very broad term. So it's very easy to think about what do you mean by exploration, exploitation? In this case, we are using this basically trying to quantify the diversity of things you work on. So if you do a lot of different things, we say it's exploration. If you just work on one line of inquiry, we say it's exploitation. It's very focused on one domain. But it doesn't mean, within this domain, it doesn't mean you don't explore. Like you are exploring within the domain, but it's just really sort of comparing across domain or within the domain. So I think that's important to think about. And it's also important to think about, sort of when we say exploitation, I think there usually is some confusion about sort of, okay, so are you saying you just keep doing the same thing? Are you saying, okay, you just Lord of Rings, first one worked, let's do a second one, let's do a third one. It's not that either, right? So exploitation is to say, within this domain, you actually do different things within this domain. So what we find is that what's interesting about hot streak, remember, so there's actually a strong hypothesis there is to say, once the hot streak starts, yes, you're at the other level, but you actually roughly stays that level at over the course of hot streak, and then you fall back to where you were, right? If you think about just the Lord of Rings example, then you would expect, okay, the first one is a hit, and then you like gradually fall back to where you were, right? And what we see is that that's not what we observe. If you look at the first half and second half of hot streak, they're very much indistinguishable. So this is sort of the idea of exploitation, is that it doesn't mean stagnation. It's like, yes, you're focused in the domain, but it's not just like doing one thing. Just keep doing that until it doesn't work. Really you continue to innovate within the exploitation domain, but it's really just like thinking about also being very focused, like this is what you do. And what's interesting then, I think that's sort of, okay, being focused, that's not a groundbreaking idea, like who doesn't know be focused would be useful. But I think what's also useful here is, if you just focus, you didn't have the exploration before, it didn't quite work either, and then you look at all these examples of, Jackson Pollock or, Peter Jackson. Before their hot streak, they tried a bunch of different things, and they did so actually is quite unusual than their typical style. So they actually did more exploration than they would have otherwise. So I think that sort of, at least for me, was quite useful to think about sort of my own career. As you know, like a lot of my projects is very much self-serving. So it started with some question I want to understand, and then sort of would basically start investigating. And so I think maybe that's something that will be useful to think about,
Thanks.
All right, and I'm stepping in for a second. Yeah, so we have, I guess we could, a few more minutes. So let's try to, if we can, a couple short questions. Sebastian, I think you're next.
So first of all, thanks for the talk. Amazing stuff. I wanted to ask you to speculate a little bit about the connection between this work and what we saw with James' work before. What happens during a hot streak with your team? Is there any orchestration between individual careers and the careers of your larger team? Thank you.
Yes, a great question. What did he talk about? Well, I wasn't in his talk. We should have coordinated. I know. It was all James' fault. Is he still on here? If not, then it's all his fault. It was but yeah. So in the paper we had a whole figure about this. I didn't cover this. It's very a good question. So we can't really look at the teams in the artist setting, for example, because they're still working in solos and so on. But we could, however, measure the teams and collaborations in science, because thanks to a recent paper we published with James about teams, we actually have a very clear hypothesis to test. In 2019 we published another paper about small and large teams. I don't know, did he talk about that work? Okay, so it's a small and large teams, and then that's kind of interesting because it tells us small teams is the one that generates ideas, right? Large teams is the one that solves problems. So then if you look at, okay, for scientists, when they're before a hot streak and after a hot streak, they're more likely to engage with small or large teams. So what we find was very clear pattern was included in the main figure as a paper, is that this kind of pattern, right? Before hot streak, individuals are more likely to work with small teams and smaller than they used to typically. And then during hot streaks, they're more likely to work with large teams. So in some ways, sort of, it is a demonstration that a change in productive strategy in thinking about engaging small teams to generate different hypotheses. And there's different kinds of small teams because they are exploring different things. And then during hot streak, they're very focused, but they're doing so with larger teams that's sort of basically implementing this kind of ideas. So that's kind of what we find, and it's very consistent with the earlier paper that we published. Basically, we're trying to say, okay, so if this is correct, then we have this paper that should actually make a prediction that we should test. So we did. I should have probably talked about that for the limitation of time. Okay, great question, Maria.
Hi, thank you very much for the very interesting research. I find it very creative that you picked to compare directors and artists with scientists. That gives us a lot of new insights into this topic. I just have a question, and I don't know if your data is also showing like a Matthew effect, and that you're like it's reflecting also the fact that after your first hit, then you probably get funding easier, or support or community like renounce on that specific area, which then increases your chances of in that area also getting a second hit, because you're getting funding for that kind of thing, and also respect or recognition, and then you go on that. So it's not necessarily that you're only measuring the cognitive development of the career of the scientist, but also institutional effects that the first hit produces. Like, and then assuming these results into or integrating these results into policy making is like, well, if like somebody gets a hit, then they probably are going to get another hit. What is the tautological thing of if you invest in somebody, then well, yeah, because they get funding and support, they will produce a second good thing. Like, it's not tautological to a certain extent. Like, how can you measure that without this element? I just see it a bit hard. That's it.
Yeah, it's a great question. We can actually measure this. This is another paper I didn't talk about. It's right now waiting to be submitted. It's a great question. We can actually now, thanks to dimensions, as you guys know, probably now, thanks to dimensions, we actually now have the funding information, right? We have the funding, so we can actually measure explicitly what you tested. What you're asking is, you know, whether there's a Matthew effect, you had like you had a big hit, the funding comes. And the backstory, interesting backstory of this was, this question came up when I was presenting to NIH. So I was at NIH, I was doing a keynote to all the program directors, including, you know, Francis Collins and so on. And somebody in the conference, in the audience, stood up and said, you know, I know exactly where how House Week happens. You know, it's 5 years because we funded it. You know, like House Week is 5 years, is NIH funded it. I was like, okay, that makes sense. So why don't we get data and just measure when you got a funding, when this House Week occurs, and see if that's exactly overlaps, right? And so what we see is that, you know, once we apply the data, we see a complete opposite pattern. What we see is that the funding arrives precisely when the House Week ends. Okay, so once the House Week ends, that's where the funding, all the funding got showered into that individual. And that makes a lot of sense, right? It's consistent with NIH's emphasis on preliminary research. But at the same time, you know, I think NIH almost had a heart attack when I showed them this. But at the same time, it raises the question of, if we are rewarding past success, are we funding for retirement? So I think that's kind of a very, so it's a very great question. I think, you know, basically we're supporting the Matthew effect. And so in this case, it's not like right after you have the first big hit, the funding comes. The funding really comes after you show one hit after another, multiple years. And then the funders are like, okay, let's fund you. You're like, you have shown it. But then your House Week ended once the funding arrives. So yeah, so I think this House Week idea basically raises broader questions on how do we think about science funding. For example, I think this exploration followed by exploitation dynamics, I feel like we haven't talked enough in terms of how to think about the sequence of exploration followed by exploitation, right? If you think about funding, you know, there are fundings specifically for exploration, such as HHMI funding. there are fundings specifically for exploitation, such as career awards. But are there fundings for exploration followed by exploitation? Are there fundings to say, I want your first 2 years to do just exploration and then 3 years of exploitation? I'm not aware of any. Please let me know if you are aware of any that's similar. But I think the broader question is, how do we facilitate this? Similarly, for a tenure track, which is 6 years, they usually have like either 2 reviews in the middle or 1 review. Like a catalog is 1 review is 3 plus 4 is 7-year tenure clock for a lot of junior people. But these tenure reviews are basically the same. They don't think about, okay, maybe the beginning should be just exploration. We reward people based on exploration. And then the last review was about exploitation. It's not clear how do we think about this, but hopefully this will generate a range of discussions how we should think about career dynamics and evaluation of careers. Yeah.
So what should we do time-wise? Sorry, I know there's one more question, but we're running quite late.
Yeah, I said maybe let's take a 5-minute break. I told Ying already, so she knows. So if people want, I mean, I don't know about the Shun's work by any time, but
okay, and hopefully you'll be around, Dushan. I mean, you'll be able to meet with a number of the students, right? So
yeah, and then we have a panel after Ying's talk,
right, and the panel as well.
Yeah.
So yeah, so save your questions.
Yeah,
Sounds
thank
good.
you so much, Dashun. Very, very cool
Oh,
Thank you.
work. Thank you for coming. Right, let's take like a 5-minute break.